Hi everyone. So in today's video, we are going to go over this paper, Simple Scalable Adaptation for Neural Machine Translation. So the reason I'm covering this paper is that this is also a paper on adapters, which is a parameter efficient fine-tuning method. I'm covering a lot of such methods for a playlist I'm building. So this is the second in line, and I hope you like this one as well. So what's the core idea here? So right now people or so this was back in 2019, but even today, people fine-tune pre-trained models, machine translation models for adapting to new languages and domains. Suppose you have a model which is trained on a very large corpus, and then you want to train it to do, say, English to French translation. So you will fine-tune it on a smaller English to French data set. Now, fine-tuning the entire model creates copies of the entire model, and then you have to store that entirely new model. So if you have, say, a 10 gigabyte model, you now have another 10 gigabyte model once you create a new fine-tuned model. So the solution which they use, and I believe this is fairly concurrent or almost at the same time, since this was EMLP 2019, and then the whole sphere tall adapters paper was ICML 2019, if I'm not wrong. So they build these task-specific adapter layers, which can be injected, and these are very lightweight, and these are also a small fraction of the original model size, so they are quick to train. And then you can also train it to do multiple individual tasks simultaneously, which is also very interesting. We'll see how they do that. Before that, a few notes. What is domain adaptation? Since these are machine translation lingo, so I'll just go over them quickly. So at a very high level, you can think of having trained model on a very large data set of, say, translations, stuff like that, and then adapting it to a particular domain or a particular language pair. That is domain adaptation. So people usually do that by fine tuning. And then multilingual NMT is where you want to build systems for low resource languages, but you do not have enough data for them. So what you do is you perform training with similar languages. So for instance, you have two languages which share the same script or have certain similarities in the vocabulary, or for instance, if you have a language which is very influenced by another language. So like for instance, when people speak in any language today, they often bring up terms from English and similar stuff. So I hope these points are clear. So now, what is their high level setup? So it's very simple. I'll also contrast with the Holsby et adapters paper, which they do in the paper as well. So first, let's look at the figure. This is an encoder decoder setup. So this is neither the BERT-like structure which the Holsby et paper was using, nor the decoder only structure which people generally use nowadays. So encoder decoder is the original transformer architecture, and then there are still models which use it T5 and the T5 family primarily. So what you do here is first you pass your input. Say suppose you're doing Chinese to English, you pass it through your encoder, and then you have cross attention between encoder and decoder, and then you get your output. Now they introduce these adapters after your feed forward layer in both the encoder and decoder. So this is the first point of difference because in the Holsby et al. Paper they had it after self-attention as well. And also they do not train the layer norm parameters. So they say that uh, they have their own layer norm inside the adapter itself. So they have multiple adapters for different pairs, and then they can quickly switch between adapters during training based on which pair uh, what language pair does the incoming data point belong to. So you can see that after the feed forward network, you have your input passing through an adapter. An adapter looks like this. So you first have layer norm, then you have an MLP essentially, then you have a residual connection, and then you send the outputs. And now, since you are not training the layer norm, you are essentially only training these adapters. So by not training the layer norm, I mean the layer norm of the original network. You are training the layer norm inside the adapter, which is something which they introduce. So you get these hot swappable adapters because the layer norm of the original model remains unchanged. So you do not need to swap that when you switch adapters. Now, let's just look at the formulation for once. So you have the output of the ith layer, which is a dimension D vector, Zi. You first perform layer norm, then you do this down projection, apply the activation, you get the hidden state, and then you apply the up projection and add the residual stream, the residual connection, and then you get the output. So I hope their adapter is clear. Now just contrasting it for once. So in the original paper, Holzgren et al. Paper, they have it after both self-attention and feed-forward. As you can see, they do not. They also retrain existing layer norm parameters for every new domain, while they do not. So they simplify this by having layer norm only within the adapters. So I hope the high-level setup is clear. Now we'll go to the experimental setup. So I'm not a NMT guy by any means, so I will just try to explain it. My main uh, objective of creating this video was to explain this setup, since this is what is the PEFT part, but we'll just go over the results to see did this even work. So they had this 375 million parameter transformer model. And then for the two kinds of experiments, so for dataset domain adaptation, they first took this WMT English to French out of domain training corpus. And then the models which are trained on this are adapted to this English to French corpus and this other dataset. And for the massively multilingual machine translation one, they have parallel documents for 102 languages to and from English. So you have, say, English to, I'm not sure about the languages, but let's just say English to Hindi, English to German, English to French, and then back French to English, German to English, Hindi to English, and so on. This is just a data distribution. So since you have so many different languages, what is the number of samples per language. So you might wonder, why are there more than 200, like 204 bars here when you only have 102 languages? Well, this is to and from. So you have 204 pairs in total. So you can see there's a very large discrepancy, say, between the smallest one, which is somewhere around uh, 0.5 into 10 to the 4, while the most highest resource ones go all the way up to 10 to the 9 samples. So there's a large discrepancy, and then what you expect is that you can perform well on these by leveraging what you learn from these. So moving ahead. So this is a very dense slide. If the PEF part is already done, you can skip all of this if you want, but I'll just go over the results for once. So on IWSLT, which is a data set that they fine tune on, these are the domain adaptation results. The adapters match the performance of fine tuning within error margins, and they only have to use 0.11% of the original model parameters for adapters. So on the other hand, for the JRC Aquis, adapters recover around 90% of the full fine tuning without updating any existing parameters uh, and only adding 13.5% additional parameters. So you can see that there is a large difference between these two as well. So one reason which seems fairly obvious is that the pre-training dataset was also English to French, and then IWSLT is also English to French, while this other dataset has other pairs as well. So if you look at this plot, figure 2, you can see that when you have only 0.03% uh, adapters of the total model weights as adapters, you are already very close to the full fine tuning. Like you are, say, zero point 0.3 away. And then by 0.011%, you surpass fine tuning. Then for the other data set, you can see that at around 13.5%, which is the bottleneck dimension of 2048, you reach within 90% of, uh, as they claim, of the full fine tuning. So on IWSLT, the residual adapters reach within zero point 0.5 of the full fine tuning with just 0.03%, which means that their hidden dimension was just 4, while on JRC Equiz, adapters had to be increased up to 13.5% of the total module capacity before you were within zero point 0.5 of the blue range. So I hope that is clear. Then this is how much in-domain training data does the model see versus how well it performs. So you can also see that there is this LHUC baseline here. So I'll just go with that. So LHUC is basically a baseline that adds domain-specific gates. So you control the contribution of different hidden units by learning these domain-specific gates, and you can see that it performs fairly similarly when you have very few number of uh, when you see a lot less data, while as soon as the data scene grows larger, full fine-tuning and adapters uh, just shoot up, while LHUC is not able to grow. So this is what this plot tries to show. And then for the final plot, so they wanted to see how does the def performance vary versus the number of in-domain adaptation steps when you're adapting versus fine-tuning. So if you look at the curve, you can see that adapter performance uh, reaches the peak fairly quickly and stays steady. So you have almost no overfitting, while for the full fine tuning, you can see that the optimal model selection is very difficult because you have rapid overfitting on the adaptation corpus, and the blue scores also start falling after a very early peak. So that just goes to show that adapters also bring you this additional benefit. So now moving on to the massively multilingual machine translation part. It has two stages. So the first is global training, where you train a fully shared model on all language pairs. So you want to maximize transfer to low resource languages. They also have a sampling strategy, which is described in the paper. You can read the paper to go into more details about this. Then finally, they have this refinement phase, where you want to fine tune language specific adapters, because that is what the paper is for, building adapters for NMT. So you want to do that for all the high resource languages to regain the performance we lost during step one, because as has been noted, the performance for the high resource languages falls while it grows for low resource languages. So the performance jump for low resource comes at the cost of high resource ones. So this step can only be applied for language pairs learned during global training, which is like it is obvious. So multilingual models significantly outperform the bilingual baseline. This zero line is the bilingual baseline, and all the other things are relative to it. And you can see that the multilingual models are above it. And when you're translating to English, any which is this any to English, you can see that it's again much better by the end. Then for high resource languages, they observe significant performance deterioration, as I was talking about. And then for fine tuning with adapters, they also tried a bunch of different configurations. So for adapters, since you are only training a small number of parameters, you can see more data much more quickly, and hence you can also converge much more quickly. So you can see the adapter line is the one on the top, and it shoots up the fastest as well. Both the blue and the yellow, so the circles and the triangles, both of them are adapters, just with different sizes. So adapter large has a hidden dimension of, I think, 4096, and then blue one has 2048. You can also see that for most language pairs, the second stage, which is this refinement stage, converges within 20 to 50,000 steps. So that is also good because you are sort of speeding up your training without any loss, so to say. And for high resource languages, you can see that when you're translating back into English, uh, you get performance improvement by increasing the adapter size, which is also, I think, a fairly obvious thing to expect because you are sort of giving it more space to learn. A higher hidden space dimension allows you to encode more stuff, more in other subspaces and all those kinds of things. So the core idea of covering this paper was to go over this high level setup, but I hope I was able to convey the results for the paper. If you have any questions, feel free to comment down below, and I hope to see you again soon. Thank you.